Okay, gravity practice problem. We have a planet that's 5 times the mass of Earth and has a radius that's half that of Earth. We want to know how that would affect a 70 kilogram man's weight. This is obviously a gravity problem. We're talking about weight, but we're talking about a different mass of Earth, a different radius. So we can't use this equation, even though that would tell us that his weight on Earth would be 700 newtons. It's not going to work because this g value only works on a planet that's Earth when you're on the surface. So instead, I'm going to use the larger formula. The force of gravity is equal to g m1 m2 over r squared. Again, we're using this because this is clearly a case that's different than the Earth's. But then from there, we're just going to extract some of the important values from here. We're talking about how it's 5 times the mass of Earth. We're talking about how it's half the radius. So we're just going to take this equation and we're going to plug in those factors of change. This is a 5 time factor. This is a 1/2 factor. So I can plug those in into here. But let's go through every single variable and see how they're going to change. G doesn't change in the problem. It's also a constant, so it just can't change. But if it doesn't change, then the factor of change is 1. Let's say that mass 1 is the mass of the planet, so MP, and it's going to 5 times bigger. So this would be a factor of change of 5. The mass of the person, the mass of our man, I guess, MM, it's staying exactly the same because we're talking about the same 70 kilogram man. He's 70 kilograms before, he's 70 kilograms after. He won't be the same weight, but he will have the same mass. So the factor of change there is 1. And then our final variable is our R variable. And our R variable is going to half that of Earth. So if we go from the radius of Earth, we're ending at 1/2 the radius of Earth, which means our factor of change there is 1/2. So I'm going to plug all of that information into this equation, but I'm going to plug them in with the changed values, or with these factors in there. So if I go through there, that means that the force of gravity for this new scenario is going to be 1 times, in the numerator, 5, because that represents the mass of the planet, times 1, the mass of the man isn't changing, times 1/2 squared. And you have to be careful with that step because the squared is a mathematical operation we're applying to the R, and we still have to do that if we're changing the R value. So going through here and evaluating that ends up, the ones, who cares about them, that ends up being 5 over 1/4 once we distribute the half. And mathematically, if you have a fraction in the denominator, you can just multiply the reciprocal times the top. So that would be 5 times 4 over 1, which means that he actually weighs, the factor of change of the whole force of gravity is by 20. So if he weighed 700 here, he now weighs 20 times 700. He's all the way up to 14,000 newtons. That's his weight on this planet. This is his weight on Earth, his weight on that planet. So key skills is definitely using the appropriate formula, figuring out how to plug in those factors of change, and then just some algebra to clean it up and get to our final answer.